Which I am, of course, doing.
Of course, yes. No, all of us are very studious. We're not forgetting to do any of our work. Yeah, so let's do chapter 4. Let's start with that, and we'll go from there. So it's 2 pretty short chapters, but they're kind of all about Python. All right, so let's learn more about Python. Data types, very important. If you've taken another computer science class, this will be very familiar. In Python, it kind of blurs the lines between like what type is what, and this is chapter 4, so please read chapter 4. Yeah, so the spiel for this slide is when you say something in Python, it gives you an answer back and it knows what kind of thing that answer was. So like, there's different kinds of numbers, right? In Python, the same is true. There's a different type for whole numbers, and then there's a different type, we say, for numbers with decimal places. And let me prove that to you. Python can tell you the type of things. So let me prove to you that, like the number 42, if you type that into Python, the type of it, another like a synonym for type is kind. The kind of thing that 42 is it's a whole number. Another name for that is an integer, which Python abbreviates to int. So Python knows that a 42, if you ever see that or you ever result in that, it is called an integer, all right? And yeah, int and float is the other one. But let me prove that to you real quick, and then I'll explain more. So let me make, in my session, a new notebook for chapter 4. Cool. I don't need these open. And so if I just type 42, of course the result is 42, but Python knows what kind of thing it is, the type of that thing. And you can ask for it by calling the type function. You can say, hey, what's the type of 42? Like, that's an integer, int. All right, so it really knows, it's just not telling you unless you ask for it. All right, so that's what the type is. And the types kind of tell what you can do to something. Another kind of numeric type is numbers with decimal places. So if you type 3.14, you have a result that results in a number with decimal places. That is called a float, which is short for floating point. If you've heard of that, go look that up. It's a kind of way to store numbers with decimals on a computer. It's called floating point numbers. It's like secretly stored in scientific notations, like the decimal point can float around, kind of. So that's how that works. And yeah, it's like, what's the type of 42.5? It's a float. Yay. And the second you know what kind of thing you have, that kind of tells you what you can do to it. All right. So certain functions only do math stuff, right? And so they're going to need numbers. Other kinds of things are like text, pieces of text. And so we'll have to deal with that. Yeah, functions like, that you can call the round function on a number with decimals, right? And then you can ask for like giving back with that many decimals. So it doesn't really make sense to call round on an int already, because round is like the whole point of round is to do stuff with floats. Does that make sense? So like you need to know the type involved, and like functions themselves have types. What's the type of round? It's a function, which is interesting in itself. And so yeah, the kind of thing you can do depends on the type. All right, it's like integers and floats. You can do math on them. You can combine them, of course. Be like, what's 1.5 plus 2? That's 3.5. So it took an int and a float, and you can add them together. The plus knows how to deal with both. That's kind of interesting, right? There's that. There is like division. If you divide 2 ints, you get back a float. Because sometimes it might be 0.5 or something. So the slash gives you back a float, even though it took 2 integers. Do you kind of see what's going on there? The types involved in the operation. So that's wonderful to remember. And yeah, another thing that I guess you can do to anything of any type is to shove it in a variable. Right? You can make a variable and you can say, hey, x. Please be like 42. So you can put a value in a variable, and the type of that variable is the kind of thing that's in it. So I can make x hold 42. Hey, x, be 42, please. And then I can do math on it, of course. Results in integers. Like, what's the type of x itself? It is an integer. It is the type of thing that it holds. Okay, the kind of thing that it's holding on to. Does that make sense so far? It's just everything that you have in Python. It has a type attached to it. What kind of thing is it? Is it a whole number? Is it a number with decimal places? And we can go from there. And you better believe I can change the values of variables. I'd be like, x, hey, be 3.14 now. And so if I run that line, I've just done this, right? Hey, be 3.14. And so now the type of x has changed, hasn't it? Which is disgusting if you're coming from a language like C++. So now you can ask, hey, what's the type of x? Now that I put 3.14 in it, oh no, it's a float. All right, so it's changed. That's not good, but there's a lot to keep in your mind, okay? What else? So yeah, floating point types. The float type comes from the word floating point, and it's secretly stored in scientific notation. So you can give it scientific notation numbers and it's happy. So like the number 5 times 10 to the 6th or something. The shorthand for that in float land is you say 5, you say E, and then you say 6. So some calculators work like this, I think, probably, right? Maybe we've seen that. So you say 5e6, it becomes 5 times 10 to the 6th. So 5e6, that is a float. And that does the work, okay? What do I want to do here? Yeah, so you want to see something weird about floats? This is making enough sense so far. So ints and floats, 2 different kinds of numeric types. I still need to show you other types, of course. There's stir, there's bool, we'll get to that. But a weird thing about floats is your computer only has so much memory in it, so it can only store numbers to a certain decimal place precision. And they picked, like a bunch of people got in a room and they decided what is the precision of a float, and you get about 16 decimal places of precision. So if I say 0.555, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, a lot of 0.555s. If I subtract from that, all that, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, the answer should be negative, yes? The answer is 0. So it's forgot about those decimals at the end. Python can only store floats with a certain amount of precision. You get about 16 decimal places of precision in whatever exponent you were in. So it's secretly scientific notation, but like you get 16 digits of precision in that scientific notation that it's secretly storing things in. All right. So moral of the story: floats are not perfectly precise, but ints are. You can have as big of an int as you want. Floats are not perfectly precise. You only get about 16 decimal places of precision, we say. Can't be more precise than that for a float, okay? Integers, however, as precise as you want to be. So like 2 to the 100th power is like, that's cool. 2 to the 1000th power, sure, I'll just make enough room to store that big. So that's pretty nice. Integers are precise. So that's one difference between those two types. And yeah, but it works. Like you do 2 to the 1/2 power, so that's the square root of 2. It'll give you that much precision. That's why it doesn't keep going. It's like that's as much as it's got. Okay. Likewise, again, like this comes up. So what you really want to do whenever you do math with floats, you kind of want to round the answer usually, because here's this again. So 2 to the 1/2 power. So the square root of 2. What should be the square root of 2 times the square root of 2? Should be 2 again, yeah? No, it's not. So it's lost some precision, okay? It's lost a little bit of precision. It couldn't store it all perfectly correct. But if you rounded this, of course, to like 8 decimal places, it would be 2.0, yeah? It would be 2.0. It would be happy. So that's probably what you should be doing, okay? So those are our numeric types, ints and floats. Make enough sense, the difference between them? So yeah, there are other types, of course. There are things between quotes are text types. So it's called a str in Python, which is short for string. Think of it like a string of beads on like a friendship bracelet that you took to that Taylor Swift concert. You got like a bunch of letters. So a string, str for short, is anything that you put between quotes. All right, anything that you put between quotes. The type of that is a str. It means string. It just means text. All right. So what's the type? And it doesn't matter if you have double quotes or single quotes in Python. Everybody's happy. Str. Everybody's happy. Different operations work differently on different types. That's the moral of this story. That's the slide that that's the topic of this slide, kind of. So there's a plus operation, of course, on ints and floats, and that does no numeric plus. There is also a plus on strs. You can add the text together. So I can say, hey, data plus space 8 with double quotes for fun. This is not going to do math, but it's going to add the strs together to make a bigger string, bigger stir. Does that make sense? So it's a different kind of plus. Python saw, okay, you're doing plus, but it needed to know the types of things involved to know what kind of plus to do. All right? So it needed to know what kind of plus to do. And so be very careful. If you have like the number 4 and the number 2 as strs, it's going to make the stir 4-2. It's not really a number. I hope that makes sense. All right? So that's interesting. And yeah, different things happen on different types. And we know from before, like, you have to like be very careful when you're making stirs, and like you have apostrophes. Can't do this with single quotes. This will give me a syntax error because like I just ended the stir with that apostrophe, right? With that, it's really just a quote. And so one way to solve that problem is you can what's called escape your. You say backslash that, and it turns into a real, just normal inside of a stir quote. And you just gotta do that every time, which is a little disgusting. But like that turns into this kind of stir. But you could have just done it with double quotes. It would have worked out. But sometimes like you have both single quotes and double quotes in your stir, and you're gonna have to use a backslash to like, it's called escaping that part. It's like, no, I'm still in the stir. I'm still in the stir. I'm not done yet. Make that actually be a real character. So the backslash quote turns into a normal quote. Okay. So I think that is what I wanted to say about all these operations. So that's stirs. Plus works differently. There's other things that work differently. There's a multiplication. You can multiply a stir by a number, and it duplicates that thing. So like there's other options there. But now I've got int, float, and stir. Questions about those? Different types, different things happen. And then finally, if you do some sort of comparison in Python, the answers are, instead of yes or no, in computer science and Python land and data science, we say true or false. So true is yes, false is no. All right, so you ask, hey, Python, is 4 less than 5? It will do that for you, and it'll be like, yes, it is. So it gives back true. It says true for that, okay? And so the type of true, type of the result of 4 less than 5, it's called a bool. It's short for Boolean. It comes from a person's last name. George Boole invented this kind of math. And so like that's a yes answer. The no answer would be false. All right, you say false. So try that. Try 5. Hey, is 5 less than 4? It would tell you false. I think that's what I wanted to say about all that. So yeah, those are 4 very important types in Python. You've got int, float, stir, short for string, and bool. Any questions about those? And they work differently, right? A yes or no answer, that's completely different from a number. Yeah. Sometimes you want to convert between types. Sometimes you have one kind of thing, you want to have it be another kind of thing. So this is very useful. Like if you give an int, you just kind of call the type that you want as a function. That's how you do it. So like I have an int 42, I want to make a stir out of it, so you call the type you want as a function. It's like this will turn it into the stir 42. Does that kind of make sense? That's what it will do. If you have a stir but you want an actual number to do math or something, then you could do the opposite. You give the stir to the int type. You give it call it like a function. And that will return the int 42 that you can then do math on, right? Because it's different. Math on stirs does not do actual, it should have been 6, right? It's not, though. As stirs, it's just going to add the characters together. So that's important. And then like you give an int to float, it'll convert it, right? It'll make it 1.0. Yay. I hope that kind of makes sense. That's how you could do that. And that is necessary. That kind of type conversion is very necessary when like you want to build up an output to show to the person who's like using your program, the user of your program. So like the answer is colon space, and then you do like a plus to add the stirs together, and then like the answer is 2 plus 2. But this won't work because what I'm trying to do right now is on the left side of this plus, I've got a stir. On the right side, it's going to calculate as an int, right? And Python has no clue what to do. So it's like concatenate just means bring the strings together. So I can only concatenate stir to stir but I've got an int on one of the sides. So we have to convert. If you want to turn this 2 plus 2 answer into a stir so that you can do something like we did here, then you have to do a conversion. Call the type that you want. So call stir on the answer. Okay? So like I've got 2 plus 2. Oops. I've got the 2 plus 2. I can ask for the answer to be a stir by doing this. That'll turn it into the stir for, yeah? And so then I can make this happen. Boop. And then that will work. Does that conversion process make sense to us? Python is very picky about those types involved for plus on stirs. This side needed to be a stir, and we can make it that, though, by asking that type to build it for us. So that's type conversion. And that's very useful. All right? Yeah, so likewise, you probably didn't want to do this, because that would make not 84 probably like you wanted it to be. If you had 2 stirs, then like you were reading a file or something, like you'd always only get stirs out of the deal. You can convert those things. So there's a big difference between this plus and this plus. I can turn those stirs into ints and then do the math. It's a different plus at that point, yeah? So Python has this idea of data types deep down inside of it, and it's thinking about them, even though it doesn't show them to you unless you ask, and you call that type function, okay? Okay, I think that's what I wanted to say about all this. Any questions about that so far? Kind of see the difference, the usefulness of it all? All right, I have a question for you guys, and I'd like to know your intuition. I don't want you to go to Python, please. So please, we'll go to the ByClicker page. I got 3 questions for us, and we can say hello for a little bit. That's fine, but let me start the question, and we'll set it up. But please go to the ByClicker page once you've done attendance. I've got 3 options. So let's say we do these 3 lines, and they look a little weird. So I'm asking for 2.5 to be an int. I'm asking for the stir 42 to be a float. I'm asking for the stir hello to be a stir again. What do you think happens when I run each of those? Your options are A, B, and C. Do you think it's going to be an error? Like Python won't let it happen? Do you think it's not an error and the answer like actually makes sense? It's still, I can reasonably appreciate the answer that Python's going to give me back. Or is it not an error, but also you're going to get a weird result that you weren't expecting? All right, so those are your 3 options. What does your intuition say about each of these? Please discuss with the people sitting next to you. Say hello, talk about your weekend, and then try to get all 3 of the answers decided on, and then please enter in your answer to question 1 on the ByClicker page, please. Yeah, what do you think should happen? What does your intuition tell you? Can you convince your neighbors that you're right? Do you think it knows? Maybe it doesn't know.
I think that there's strings are from chords and floats are from vectors. Okay.
Mhm.
Yeah, sure it's not. I think the integer is gonna give us a weird result. You're converting a float into an integer. Maybe it'll like. Oh, it starts off. Yeah, because see, it's in the parentheses. That's what it starts as, and then the thing is what you're trying to turn it into. So you used to put everything parentheses. That's weird, but.
So give me another minute to think about it. What good thoughts?
Are you going to language? Excel. Oh, Excel, yeah. That's all right. I mean, Excel is a skill in itself. It's fun. It's fun until you don't know what's going on anymore, and it isn't so much fun. People believe it could work. When you make
So
when you make anything work, it's fun.
So the integer would work if there was no parentheses. It's just int 2.5. Integer would work if there was no parentheses.
Oh no, it's not that this isn't working, it's that you're trying to convert something that it isn't. And so an integer is like a full number, right? But this is a decimal. So it's gonna convert this decimal into a full number. No, it's okay, you just learned it, we got the slides earlier.
Yeah, it was 2 slides ago. You're fine.
No, I should know what an integer is. I'm a math major.
Well, I forgot, so. Thanks.
All right, friends, let's come back together. Let's see what we're thinking. So let's remember what these actually do. Like sometimes these work, right? Like int of the stir 42 will totally do something normal and make sense. Stir on the number 42 will turn that into a stir. Float on an int will make like a bigger float out of the deal. That's fine. And these are kind of weird. All right, so enter in your answer for number 1 because you can only enter in one answer at a time on the bike collector page. But hopefully you got them all ready. And let's see what we're thinking. And then we'll see if our intuition is correct. All right, that's where we're going with all that. Boop. So int of 2.5. So I'm trying to use a float to make an int. All right, to make an int out of the deal. Let's see what we think. Nice. We're thinking C. Okay. Cool, cool, cool. I think it's not an error, but we get a result that we weren't expecting. I guess if it's not an error, kind of what will happen is it's either going to give you 2 or 3, right? It's either going to round or like it's got a 2 in it. I think those are your 2 normal answers that you might get out of this. Do we agree? I don't think you get anything other than that. And so like we got to figure out, okay, if it's going to work, which option is that going to be? So let's see. Well, let's see what we're going to do. So int 2.5, it's going to be 2. It's going to be 2. So it's not going to round. Like that takes more thought in Python. To convert a float to an int, it's just going to chop off all the decimals. Even if it was 2.99, it would make it 2. Does that make sense? It's weird. I definitely agree that the answer should be C. We're not expecting this. And so, yeah, if you want to round something, you got to use the round function. You call int on the thing, it's going to chop off the decimals because there isn't any room to store. It's just going to forget about it. Okay? That's weird in itself. So yeah, we get a 2 out of the deal. All right? Awesome. Okay, what about number 2? What do we think for that one? And that was float of the stir 42. I guess the question is, like, will this turn into, because what we would like is this would be the float of 42, right? Does Python know? What do we think? We think it's an error, and I agree. I guess with if you equip Python with AI or something, it can turn any nameable number into a number, but that is not baked into Python, so this will not make sense. Python will get confused and it will not work. So again, float 42. It's like, nope, can't convert string to float. If the string was like a string with numbers in it, like this would have worked. Float of the stir 3.14. Then of course it's happy, because like that's easily convertible. But 42, no, it's unhappy. Okay, last one. What do we think? What does our intuition tell us should happen for stir hello? It's already stir. Is it going to complain and be like, hey, why are you trying to convert? That's one option. That would be A. Or I guess your other option is like it adds some more quotes outside of it. Like you got a few things. Like either it's an error, or Python gets confused. Like why are you trying to convert? It's already stir. Maybe it adds another quote. Like it started with hello. You made it another stir, so it adds another quote or something. I guess your other option would be that it just doesn't do anything. Gives you back the same stir, right? I think those are your 3 options. I think they cover A, B, and C. What do we think? Nice. We think B, and I think the same. Good. I think we all did attendance too, so that's perfect. Awesome. So yeah, it is going to be B, it is just going to not do a thing, anything at all. So you say stir on hello. It does not change it. It does not complain. Because sometimes you don't know if you had a stir or not. It's like, let's be safe and be sure. It's always good to defensively program. It's like defensive driving. So yeah, I think that's everything. Do the answers make sense to us? Maybe not the int 2.5, but we can remember that from now on, I think. Definitely wanted to show that to you so you don't discover that on your own. It's a little weird. Yeah, I think that is most of what I wanted to say. Yeah, let's go back to comparisons, because that was another thing. Like, you do a comparison, the answer is yes or no. Python can like see if one thing's bigger than another, stuff like that. Here are all the comparisons, the major ones that you can do in Python. You can ask for, hey, is one thing less than the other? Is one thing greater than the other? And like this would give back true, we saw, capital true. This would give back false. So try that and get back false. Like, hey, is 2 less than 3? 2 less than 3? True, yes it is. Is 3 less than 2? No, it's not. False. So it says that true and false, capital T, capital F, for yes and no. And then the others are there too. We do a less than or equal to like this because it's hard to type this character on a keyboard quickly. So we just say less than and then an equals to sign. So like, hey, is 2 less than or equal to 2? We write it like that. Okay, and that would be true. Greater than or equal, same deal. Is 3 greater than or equal to 3? Is 2 greater than or equal to 3? No, false. Equality check is an interesting one. We're going to use a double equals to check for equality. Are these two things equal, yes or no? All right. Is 3 equal to 3? We say double equals. Is 3 equal to 3? True, yes it is. Is 3 actually equal, yes or no, to 2? It'll give back false, no. Why do you think we use a double equals? So we could use a single equals. Or could we have? Yeah.
Want to think that 3 actually equals 2.
Yeah, because we have that already for variables. Yeah, that's the problem. That's why we needed a double equals. Because if you do something like this, you're not asking Python, hey, is x equal to 42 right now? You're making a variable that is forced to hold x like 42. Yeah. So because we're already using that syntax, we need a double equals to check for the equality. Because otherwise, Python thinks you're trying to assign a value into a variable. It's like, hey, is 4 equals 4? If you do a single equals, it's trying to put the number 4 in a variable called 4, and you can't have a variable called 4. It's like, no, cannot assign to a literal means like a value already. So maybe you meant double equals? Yes, I did. So, hey, is 4 equal to 4? Yes or no? Yes. I'll get back true or false. Remember the double equals? Single equals is for assignment. I really wish they didn't use a single equals for assignment. I really wish it was like x, like a little arrow, 42. You could have done like a less than and a dash. Some languages do that because it's not really mathematical equality. But that's what we're stuck with in Python. Okay, so there's that. And then likewise, for checking for disequality, hey, is one thing not equal to another? Because it's really hard to type this character quickly on a keyboard. We do an exclamation point and an equals sign. So you can ask the question to Python, hey, is 3 not equal to 2? And the answer is yes, it's not equal. So this will be true, and this will be false. Hey, is 2 not equal to 2? So you pronounce the exclamation point as not. Is 2 not equal to 2? And the answer is no, because they're equal. Okay, so that's how you check for disequality. Is 2 not equal to 3? Yes, 2 is not equal to 3. Yeah, so you got those. I think that's most of it. So questions about the comparison operators? Pretty similar. Python will do the comparison for you, though. It's nice. You can also do math inside of it. It's like, hey, is 2 plus 2 less than 4 times 7? Like, it'll do it all and like give you the final answer of yes or no. You can also, which is nice because in other languages like C++, if you're coming from that, it doesn't work. This works in Python. You can chain, like in math, like in actual math, you can chain comparisons. Hey, is 1 less than 2 is less than 3? True. And I'll check like, hey, it'll check both, right? Is 1 less than 2 and is 2 less than 3, right? So that's nice. You can chain those. And yeah, it works for different kinds of types. These comparisons, they work in the way that you would expect. So like, of course, you can check strings for equality. Like, yes, high is equal to high. But you can also check them for order, which is weird. It just so happens to be true that high is less than mom. And the reason this is true is because the less than on strings, on strs, is comparing in dictionary order. So high would appear in the dictionary before. It's less than mom in that sense. Okay, so there's that. And yeah, the type of trues and falses is bool, short for Boolean, if you want to look that up. Okay, so yeah, some of the types are weird, but you get used to them. And I think that is what I wanted to say. Any last questions about comparisons? All right, because now I have a question for you. Let's see. Do you remember the math library? You say import math.
Mm-hmm.
You can do stuff. Import math. You can do math.square root of 2, like that would work. Give you back the square root of 2. There's a function in the math library called floor, which is a cute name. Math.floor, what it does is it shoves a number down to the nearest, like it does kind of, at least for positive numbers, it does the same as integer, like call the function int on the thing. Math.floor chops off decimals. So math.floor, you call it on 2.6. It does, like, this is the mathematical operation that describes what int is doing in this example. It is shoving the number down to the floor, shoving it down to the closest, to the next whole number. So math.floor on 2.6 would give you back 2. It's just math.floor on 2.999 would shove it down to 2 as well. But math.floor on if it's already a whole number, it would keep it that whole number. It's not going to push it down into like 41 or anything. So it stays 42. So math.floor is an operation that kind of shoves a number down to either the same number if it's already a whole number, or like the next whole number below it. Does that idea make sense? There's a similar one called ceiling that's pushing a number up to the ceiling if it's to the next whole number, but floor pushes it down. So 2.6, even 2.999 turns into 2. Floor on 42.0, it's going to stay 42. Okay, so that's math.floor. The round function, to round to the nearest whole number, can be implemented with math.floor. Can you complete this? So I want you guys to discuss and see. If you want to round the number x to the nearest whole number, like if 2.4 should go down to 2, blah, blah, blah. 2.5 should go up to 3. 2.6 should go up to 3. So think of all the values you can put in x. What can you do with math.floor and a plus on that x to turn this one into 2, but turn these guys into 3? All right, there's a way. Try to discuss and think about that. So that's one way to do some math and do some cool things, to implement an operation we know, to implement rounding. Can you see what needs to be filled in there? Yeah, play around with that.
Anything. Maybe make it go, because adding 0.5 into 2.9, make it 3.4, but
There's one.
Are we getting that? Yeah, think about it.
Will we be using math notebook at all in this class?
In the math library? I think so. Yeah, we're going to need it for sure later in the class. Though I think we could implement a lot of it ourselves. Some things are going to be useful eventually. But I'll never force you to implement like sine or something. Like we'll just use the one that's made for us. Yeah, I think we're going to use at least the power function. Okay. What's the number that fills in the blank? It is a number, by the way. See that? You get it? 0.5. Good. Does that make sense to us? That is how you can implement this math.floor function, or math.round or something. There is a round function. I guess that's the one that's already baked in for us. So you can implement the round function if you're only going to ever round to the nearest whole number, like this. Because you give me 2.4, if I add 0.5 to that, I get 2.9. Hard to write a 5. I get 2.9, and if I take the floor of that, the mathematical symbol for the floor operation is really cute. It looks like this. You're shoving it down on the floor. And then that will turn into 2. Nice. But the second you give me 2.5 or something bigger than that, you add 0.5 to that, then I get 3.0. The floor of a whole number is still that whole number. And I just get 3 back. So you can implement rounding in this way. That's so fun. Because we're chopping off, we're shoving it down to the nearest whole number. Shoving it down, always downwards, is what the floor operation does. And that is the nearest whole number to 2.4. That's exactly what we wanted. So that is why you can use floor for that. It's very useful. Other questions about that? So yeah, you can, that's kind of like how this all works. All these libraries are implemented by people thinking hard about like, okay, how can I use previous things to build up the new things? And just keep going. That's how you make an entire program. All right. I think, yeah, that's most of what I wanted to say about the slides. Are there any last questions about any of this data typey stuff before I get ready to switch gears to the next chapter? 2 short chapters today. I do still have a few things that are about data types that I want to teach you. So I still have a miscellaneous section for this chapter. Miscellaneous things I need to teach you. So if you have a stir, there are some things you can do to that stir. There's a dot upper operation on it. It's kind of like the tables. So you can do give me dot select, dot where stuff. So you can do dot stuff on stirs too. If you say dot upper, it converts anything that could be uppercase, like letters, to uppercase if they're not already. So that's that one. There's a replace operation on stirs. So hitch, hiker. A fun operation to do that is you can say dot replace every time you see hi with ma, and this will turn hitchhiker into matchmaker, which is cute. So all the hi's turned into ma's, and so that's what dot replace does. And yeah, then we have math library stuff. So you know that there are, in addition to like math.square root, there's functions inside the math library. You got to prefix it with the math dot if you do it this way, if you import it that way. There's also hard-coded like variables within the math library so that you don't have to make them yourself. So there's math.e, the constant e. There's math.pi to as many decimal places as a float will allow. There's that. And then what else? So yeah, we talked about round. Just to remind you, you can round a number to a certain number of decimal places. If you give nothing else to round, it rounds it to the nearest whole number, maybe using the floor operation. But if you ask for round it to like the nearest 2 decimal places, you can give a second argument option to round it to that, and it stays afloat at that point. So it's that one. We know about math.floor now. That's cool. 2.72 makes it down to 2, even 2.99, but math.floor on like the whole number 2 just keeps it 2. Encourage you to look at the documentation page if you want to learn more about the math library, Python math. You just search for that. The first link in theory should be the Python documentation page, python.org. You just scroll down, you look at all the cool things, and so you can click on them and see what's in there. So there's all those. Yeah, the opposite of floor is ceiling, which is cute. You can shove it up to the ceiling. So math dot, it's seal for short. On 3.14, that'll turn into 4, right? That'll end up being 4, which hopefully makes sense. And then yeah, the last miscellaneous things I think I already kind of showed you, but like if you have a string and you need like your heart is set on using single quotes, but you want to put single quote characters within that string, remember that you have to what's called escape them. So like this won't work because it thinks that the stir ended right here, right? But you can say to Python, no, that's part of the string. I want that to be an actual quote character. And so your options are use double quotes, but sometimes you want single quotes and double quotes in the same stir, so you run into the same problem. What you can do is you can escape that quote character, is what we call it. And so instead of just a normal quote, you can say \quote, and this will turn into just a normal quote character, but within the string. So the backslash goes away. It's just saying, I want to do something special with the next character. So that turns into the actual string can't still, okay? And yeah, I think the last thing that I want to say is there is a len function. I can't remember if I showed this before or not, but the len function on stirs, at least, will tell you how many characters are in that stir. I guess we used that on the first day for sure. Yeah. And those are the miscellaneous things from this chapter that are going to be necessary to complete a future assignment based on this chapter. And I think that's what I wanted to say. Any last questions about chapter 4, data types? So remember, the operation that you're using probably depends on the type in some way. Like the plus on stirs, completely different than the plus on ints and floats. And that's going to come to bite you one day if you forget. So do remember. Okay, so that's chapter 4. Let's do chapter 5 real quick. So chapter 5 have even fewer slides, but there's going to be more practice time just in the notebook land. So chapter 5 is on a topic called sequences, which is very, very important because like you make a data set, you've got a bunch of things, you got a big sequence of data, right? So we need to be able to like modify those sequences, mess with them, ask questions about them. Very, very important stuff. So let's work with sequences now. All right, so this chapter 5, please read chapter 5. You'll get my thoughts regurgitated again. It'd be very helpful. Yeah, so let's talk about what we're doing here. So the quintessential type for sequences is called an array in Python. All right, so an array is a kind of type in Python that holds a sequence of values, so like numbers, a bunch of stirs, a bunch of floats, whatever you want. And this is how I'll draw them. Like you can make an array and give it a name, call it like A or something. Call it like A or something, and then you can put a bunch of stuff in A. It's a sequence of things. Let's say we put like 42, 43, 44. It doesn't have to be in order. 45, and then like -1. And this is how I'll draw a sequence, and you kind of think of it in this way anyway. It's a bunch of things. There's a certain order to them. Like this is the 5th thing, for example, and yeah, it's a big, like the whole thing is the array. It's just like a big type that holds little inner types. Yeah, that's what it's doing. So it's a type that holds other types. And when we make arrays, they come from the NumPy library. That's separate from the data science library, but it's going to use them anyway. So the NumPy library gives us some really neat array types that let us like do math on every element at once of the array, every piece of it, which is nice. And then when we do data science-y stuff, like we make those tables with the capital T's from the data science library, when we do that, it's really using these arrays deep down for like the rows, and really it's the columns of the table. Okay, so let's make some arrays. I'll make a new file for chapter 5, and I'm going to include every piece of the data science library. So from data science, import star. So I don't have to say like data science dot table. I do it this way. So include everything. And then the way that you make arrays in this library, you can also look at our documentation. If you want to follow along or look at the documentation, it's this JupyterLab page on our canvas. And if you scroll, it's these 2 Python reference files. All right, you can also like play along in one of these temporary ones. Recommend the second one, but either of these, whichever ones you want to go look at, will have information about array stuff, array functions and methods. They're in here. All right, there's a function called makeArray in our library that will make this special NumPy arrays, like it's playing nicely with the NumPy library. You just say makeArray and you give it a bunch of things, and it gives you back an array of those things. All right, so that's this documentation page. You better believe it's here too somewhere, but I don't know where. Array functions and methods, make array, give it a bunch of stuff. Chapter 5, what do you know? And it makes an array with all of those things. Okay, so I say then, make array, make underscore array, give it some stuff, 42, 43, 44, shift enter, it gives me back as one big chunk of a thing an array of all those numbers at once. And I can put all of that array, that whole sequence, into a name. I can give that a variable name. So it's a bunch of things I can call one thing, which is fun. All right. And yeah, the type of this is a NumPy array. And so ask for the type, NumPy array. Cool. And you can put not just numbers in your arrays. You can make a bunch of sequences of anything. Maybe I can say make array of Pokemon names like Pikachu and Charizard and I don't know, Squirtle. And remember that strs doesn't matter if it's single quotes or double quotes. And so this is now an array of strs, an array of strings. Okay. And it'll kind of print it back out to you in a fancy way. And you could save this around. You can give it a name. Be like, Pokemon, I like, and equals that. And then you could ask about it. You could do stuff with it eventually. But like it's there. It's saved away. The whole sequence is saved in one name. So those 3 strs are part of one name. Does that make sense? So yeah. There's that. And then, okay, this exists now in memory. It has this name. And it kind of looks like this from the picture. Kind of looks like this. This is secretly kind of what's going on. There's a way to get at each piece of a sequence, of each piece of an array, and those are called indices. Like if this was your array, it's called A or something. The first thing, this is something to get used to if you've never seen this before, but the first thing exists at index 0. We call the pieces of an array. These are all the elements, and they exist at certain numbered indices. So this is index 0, index 1 is the second thing, index 2 is really the third thing. So you just remember that, or you might be off by 1. So you can ask about, you can also ask about the size of an array, like, hey, what's the length of this array A? Python will give you back 5. So len works just as easily on strs as as easily on arrays as it does on strs. So I got this Pokemon array, I can ask for its length. There's 3 things that I put in it. And if I want pieces out of that array, I want to get the first thing, then you say it like this. You give it the name of the array, and then you say dot item, give me the item at index blah. If I can write in it. So if I say a.item 0, that will give me this 8 back. Does that make sense? That's the first thing. First thing always exists at index 0, not index 1. All right? That's something to remember and get used to. You kind of think about indices as how far away from the start do I want to go? Maybe that will help. I want to go 0 from the start. So a.item 1 will turn into and give me back the 6. That's 1 away from the start. So it's the second thing, really. Okay? So I can do that. I can ask about that. I can say Pokemon I like dot item 0. That's Pikachu. Dot item 1, and that gives me the second thing. That will give me Charizard. Wonderful Pokemon. Yeah, you can do a bunch of stuff. So I think that is the start of it. Does just the basic idea of an array make sense? You say make array to like build one, put a bunch of stuff, gives you back an array and call it something. You ask about its length, you can get at pieces of it, but it's a thing with one name that holds a sequence of items. Sequence of elements at indices, and the indices start at 0. You good with that so far? All right, just shout out if you have questions. Let's do something useful. Let's say we've got an array of temperatures. So 100. Let's say we've got them in Fahrenheit, 78, 32, -40. So here's an array of temperatures in Fahrenheit, and I can shove that into an array called that. A fun thing you can do with these kind of NumPy arrays is you can do math on them all at once. You can say, hey, give me this array and multiply it by 2, and it will generate a new array with each of the elements having been multiplied by 2. That's very useful for us. All right, so that's really cool. So you can do math on arrays at once just by using the operators that we know already, like the star, the plus, all that fun stuff. So it knew what to do, which is fun. You can, of course, ask for the length of your your array. There's 4 numbers in this temps F array. There's other ways to get that though, like the NumPy arrays have things, like they have things that you can do dot with, so like temps F. There's a dot size variable living inside of the array secretly, so that also is another way to get the 4 out. There's other things you can do to an array, and these are, by the way, they're all here. So like there are, gosh, again, array functions and methods. There's like, here's how you make an array. You can get the max, you can get the min, you can sum things up, get the absolute value of all the values at once. You can round every element in the array. Some of these start with numpy.round, blah, blah, blah stuff. But get the average or mean, get the standard deviation, we'll use that eventually. Get the square root of every element. But there's, yeah, I encourage you to read through this. Here's a bunch of them. We did the dot item. There's max, min, and sum. And there's a couple ways to do it. So yeah, let's talk about that. So you can say temps F, there's like a dot sum that'll sum them all together. So all those numbers of the original array summed together is apparently 170. You can ask for the average of all the elements. Another name for that is mean. So you can say dot mean. You can also say dot average. And you get all this. Okay. Some of these operations need to be like they're baked into the NumPy library, which we have not yet really imported. And so here's the way we do that. You say import NumPy. This is the thing that is like behind the arrays secretly. And then everybody got tired of spelling out numpy dot this, numpy dot that. So you import it as np. That's what the cool kids do. And so now we could just say np dot this, np dot that. It's better. So one thing that is useful is np.diff, that you give an array to this np.diff function, and it will give you back a new array of consecutive differences between values. So read that to get another explanation of it. Is it here too? I'm sure it is. np.diff, an array with the pairwise differences between the elements in the input array. The output will have one less of size, and will have x1 minus x0, x2 minus x1, x3 minus x2, blah, blah, blah. So an example is worth a million words. Let us do np. So this is our original array. This is temps F. Let's do np.diff on that. Boop. It will give back the following, and the way it calculated this is it did 78 minus 100. That's 22. So it did this one, 78 minus 100. Did these two differences. So it calculated one number there. It did 32 minus 78 to calculate negative 46. Yeah. And then it did negative 40 minus 32 to calculate negative 72. So it's giving you back the differences of each value, each pair of values as you go forward. And that's why it has one less result than the length of the original array. Okay? So that's the diff function. That's useful. And then, yeah, let's kind of combine some ideas, and let's convert all of these temperatures to Celsius to give them to somebody who doesn't live in the US. So to calculate to turn these temperatures, temps F, into Celsius, the formula is you'd first subtract 32 from all of them. So now temps F minus 32 is all this. And then you multiply by 5/9. So that's the weird conversion. By 5/9. Cool. And then here are the Celsius versions of those original temperatures. So apparently 100 degrees Fahrenheit is 37.8, I guess, ish degrees Celsius. 78 is 25.6-ish. 32, of course, is exactly 0. And negative 40 is the fun one. That's where they overlap, those two lines. And so negative 40 Fahrenheit is negative 40 Celsius. That's fun to think about. So that's just cold. And you could make that into a new thing. Temps C equals this. And then print it back out. Cool. And so I can use that original array, temps F, to build new things by doing array operations. And you can do math, and the math works on each element at every index. All right. Are there any questions about how I obtained this? How I obtained this new array? An array is just a sequence of values. Yeah, you got a bunch of options here, and let's see. I just want to walk you through them. I encourage you to go through that documentation page. Like, okay, I've got an array. What can I do to it? Go look at the examples. Go see what you can do. Another cool one is np.round. That will be useful for us here. There's np.round. You can also just say round. But if you say np.round, you give an array and like a number of decimal places, it will round every piece of that array to a certain number of decimal places. Because this resulting array, because it's got a bunch of repeating fractions in the answers, it kind of looks a little unwieldy, kind of hard to want to like give this to as an answer to somebody. Let's maybe round all these answers to 2 decimal places. I think that would be nice. So you can say np.round, give that sequence, give that array. And if you say nothing, it will just round everything to the nearest whole number, but you can also give it a precision. So round everything to the nearest 2 decimal places, please. And this makes a lot more sense. This looks better. This is something we, like these numbers are the ones we give to somebody in our final output. Yeah. So yeah, that's np.round. What else? There's just a bunch of little ones that I encourage you to go through, just like read about all the different array things you can do in either of these documentation pages, whichever one makes the most sense to you. But yeah, that's how you do all that. Let me show you something weird. Are we ready for something weird? I want to show you that you could do math on trues and falses, which is disgusting, but it's possible and it's going to be necessary eventually. So you know you can do a bunch of comparisons, 2 less than 3, 3 less than 4. You can get trues and falses back. But weirdly enough, and this is actually to our benefit, you can do math on trues and falses. You can do a plus on trues and falses on bools. And true in Python is going to be a 1. Python's going to consider true to be a 1, and Python will consider false to be a 0. So therefore, if I say true plus false plus true, the answer will be 2. Ta-da! That's horrible. And the reason this is going to be necessary for us is because when we make arrays, Python doesn't really, like the NumPy library doesn't really care about trues and falses anymore. It's easier to store 1s and 0s as far as it's concerned. So if I make an array of comparison results, like 1 less than 2, 2 less than 1, so it's really like I've just put true and false into the array. 8 less than 7, another false. 42 less than 43, a true. This will turn into, oh, okay, I guess it's happy. Never mind. But it will turn into an array that looks like this. And I guess, yeah, there's an update has happened. But when you do this, it's secretly being stored as the first element is a true, but it's really just a 1. The second element is a false, but it's really just a 0. And so, let's see, what's the best way for me to show that to you? Can I do like an np.round or something? Yeah, so it's really thinking about it in terms of something like this, okay? If that makes sense to you. Like, I was able to do that kind of math for weird reasons. And so it's really thinking about it in this way. Like, this array was really just 1, 0, 0, 1, weirdly enough. And so if I ask, it will eventually become necessary for me to ask this question. You can ask NumPy, how many 1s were here? How many things were true? Does that make sense to want to answer that question? Like, I've got an array of a bunch of trues and falses. I want to know how many trues were in here. Not just the size is 4, but how many trues, exactly true, all right? And instead of asking NumPy that and saying, NumPy, count how many trues there are, the operation is called count non-zero. That's right here, np.count non-zero. You give an array, it will give you back the number of non-zero, or therefore true elements in the array. So you can make an array of comparisons and ask how many of those comparisons within that array were true by saying count the non-zero elements. That's what I'm trying to get at. All right, it's not saying count true, it's saying count non-zero. Anything that wasn't 0. And so if it's just trues and falses, you have 1s and 0s, so it'll count the trues. All right, so yeah, that's how that works. I'm honestly impressed. last semester, if I just ran this, like it's been updated since then, but like if I just ran this, it would give me 1001 from before. I want to see if I can try to get at np dot, where is it? Just for fun, for my own sake, np dot array. Let's see if I do it this way, if it will give me the ones and zeros from before. No, okay, that's cool. It knows the difference now. But anyway, think of it in terms of this NP round example. Like it will work out in that way. So let's see here. Let me delete that. Oh. Yeah, I want to delete that. And then if I say np.count non-zero of this, I will get back 2. That's what I'm trying to say. Because it treats true as a 1, false as a 0. So the non-zero elements of this array are this one, and it will notice them. Okay? And it will notice that. And I think that's a good start. Does that make sense so far? It's a weird idea. But that's like the function baked into NumPy that we care about. We're gonna ask count non-zero a bunch of times in this class. It's very important. Yeah, I've also got that Pokemon array with a bunch of stirs in it. You can do stir stuff. There's a np dot character operations dot upper function. So run that on all this, and it will uppercase all of the characters in every element of that array. There's that one. And then, yeah, I think count non-zero is going to be very important to us in this class, so remember that one. One that may be even more important is a range. So here there's a, you can call it in a bunch of different ways. It's called np.arange. Can I zoom in for us a little bit better here? Yeah. np.arange. You can run it in one of 3 different ways. It takes start, stop, and step, or just start and stop, or just stop. And this will generate an array for us so that we don't have to type it in. It's very useful. Another place is here, np.arange. So yeah, you can run it in any one of these 3 different ways. I'll explain all of them. But you run it, it will generate an array for you with certain numbers in it. And we're going to need that a whole lot in this class. Okay, so let's talk about it. So the simplest way to call it is with just one argument, with just one value here. And that becomes the stopping point. So by default, the start will be 0. If I say np.arange, it's short for make an array out of this range of numbers. So np.arange 5 by default, it starts at 0, and you're asking it to stop at 5 and increment by 1s. And this is what we get back. So what happens is it's going to give you back a range. Have we seen this kind of syntax in math before? Like 0 with that kind of bracket, and then 1 or 5 with that kind of bracket? We've seen that before in math. That's what it's doing. That's what, when you ask for something, the stop point, and this is pretty much of every kind of Python function that ever does something like this, the start is inclusive and the stop is exclusive. That gives you some nice mathematical properties if they do it that way, and they did it that way. So np.arange 5, by default, it's starting at 0, and it will go to up till but not including the 5. Up to but not including the 5. All right? And so by default, the start is 0, but you can give a starting point other than 0 if you give 2 arguments. So np that will generate an array with a certain range of numbers. np.arange. So if you say 10, 20, this will give me a bunch of numbers starting at 10, up till but not including 20. Yeah? Up till but not including 20. And that's very useful. Like we got a bunch of numbers very quickly and easily out of that deal. Okay? Okay. If I want the numbers from 1 to 100, what do I say to np.arange then? What should I put here? I just want all the numbers from 1 to 100, including both of those. 1 to 101. Does that make sense to us? That's exactly right. 1 to 101. That's an easy way to get a bunch of numbers that you can do stuff with. That's given me the numbers 1, 2, all the way to 100, up to but not including 101. So that means up to and including 100, the one before it. Okay? And then finally, the last way you can call a range is if you want total control. By default, it's stepping up by 1 each time, but you can say, no, count by 2, count by 5s for me, please, by giving a third argument, and that's called the step, all right? And it could be like a float, like it doesn't have to be whole numbers. It totally works like that. So you can say np.arange, let's count from 5 to 100, so 5, 101, so up to including 100 by 5s. See how this is going to count from 5 to 100 by 5s each time. I put 101 here because if I put 100 here, it'll only go up to 95, right? Because it's going up to, but not including that stop value. So if I put 101 here, then we're set. I could also put 102, 103, 104, and 105. Anything. Any one of those would have worked. But I like to think of it as just like one more than the stop value. That makes sense in my brain. So that's you having total control. You're building up an array that has a certain range of numbers within it. So it's giving you that sequence very quickly. So we're going to need that a lot in this class to build up a certain kind of sequence. I guess the last one I wanted to show you is you can have it count downwards because the step could be negative. Like np.arange, let's count from 13 to 12 by 0.1s. So start at 13, go to, well, let me just show you how you kind of think of it. Like you can discover it together by negative 0.1s. This will almost work. So it's counting up at 13, it's counting down by 0.1s, and I want it to go to 12. So I really need to give like 11.9 or something here. That'll work. See how that's going to count from 13 to 12 by negative 0.1 each time. Yeah? That's a descending sequence. So that'll work. Alternatively, there's a way to reverse a sequence. So like you can build the normal one, and then there's a way to reverse it. So look into that. That's useful. But I think that's what I wanted to say about arange. Do you see how it's generating things for you? It's generating an array for you. Any questions about that before I show you a more involved example using that? Yes?
I can go on forever. 13, 11.9, and just incremented by like 0.1.
I think that will give me the empty array. By 0.1, you say? That will give me nothing. Because like starting here, stopping here, going by 0.1, it's like, well, I'm already past the stop point. It's up to, but not including that. And so because this is positive, it's like, all right, I'm already done. Yeah, that's a good question. Yeah, so it's giving you a sane result. It's, rather than an error, it's going to just give you the empty array. Good question. Other questions? Because I think one fun thing that we can do that I want to show us is, let's do something nice that uses sequences. Let's calculate pi together. All right, so here is one, there's a million different formulas to calculate pi, you know that. Here is one formula that's infinite to calculate pi. All right, you multiply 4 by this result of this infinite sequence of numbers added together, or added and subtracted together. So like first you subtract, then you add, then you subtract, then you add. So there's a bunch of positive terms and negative terms here. And apparently, if you do this until the end of time, you will get exactly pi over 4. Then you multiply that by 4, you get pi, right? So we know that floats don't have a bunch of precision. So let's just go up to 9,999 on the denominator. We can just stop there. That will be a very good, if we do this, if we calculate this, that will be a very good approximation, right? For pi over 4, yeah? And this is just the same thing twice, and I don't think I need it twice, as far as I know. Should be okay to get rid of that. I can copy it later if I need it. So yeah, some of these terms, and let's kind of notice what we need to do to calculate these things. Notice that like there's like a pattern going on. Like these are a bunch of odd numbers on the denominator. Like this could be considered 1 over 1, right? So this could be 1 over 1, same down here. And so it's like you're adding 1 over 1 and 1/5 and 1/9. Like you're going up by 4s. Those are your positive terms, right? Does that make sense? So those are your positive terms. These ones that I'm going in green. You keep on going. And then you've got the negative terms, minus 1/3, minus 1/7, minus 1/11. Let me use a different color for those. subtract that one, subtract that one, subtract that one. So it kind of alternates in that way, right? Kind of alternates in that way. And so what we can do, one way to do it, is we can build up an array eventually holding all these positive terms just in one array. And then we have an array holding all the negative terms. Like take these, subtract these from it, kind of. That's what we'll do. Okay? So like we'll build up just the positive terms in an array. Positive terms. And what are those? We've got the 1 over 1 plus the 1 over 5, right? Plus the 1 over 9 plus, you see the pattern? The next one will be 1 over 13, dot, 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 all the way to 9,999. I guess we're not going to use that one, but that's fine. That will be a negative term. So you get all those together, and then you subtract from it. We're going to have another way to calculate, like 1 over 3 plus 1 over 7. Those are all our negative terms. 1 over 11 plus da da da. So those will be our negative terms. And do you see if we do it up till 9,000, like the denominator being 9,999, you take all these, you subtract, you add them up, and then you add all the negative terms up and you subtract from the positive terms. Do you see how that will turn into this, like this stuff in parentheses? And that's a good approximation to a decent number of decimal places in theory of pi over 4, and then we multiply it by 4 and we get pi. I think this is not the best approximation, so we'll get it to a couple decimal places, but you need to keep going for quite a while to get a better approximation or use a different formula. But this is like an easy formula to do now that we know this stuff. So, okay, I would like to make some sequences to make this easier. Do you see how if I start with the sequence 1, 5, 9, 13, like that will eventually get me to 1 over 1, 1 over 5, 1 over 9, like I could do it that way? So let's try to make that happen. So let's get with the, let's make a sequence of the denominators I need for the positive numbers. I need 1, then 5, then 9, then 13, and so on and so forth. You keep on adding 4, right? Then I need 17, blah, blah, blah. So let's make that happen. Those are my denominators. I want np.arange starting at 1, right? 1 over 1, then 1 over 5, 1 over 9, up till 1 over 9,999. So like, and including it. So like go up till 10,000. Yeah. And then increment by 4s each time. See, I get 1, then 5, then 9, blah, blah, blah. Up to 9,997, which is the correct last positive term, up to 9,999. These will be my positive denominators. Posdenoms, let's call it. So that's going to give me the 1, the 5, the 9, the 13. I can do 1 over each of those. I can do 1 over each of those eventually. But does this make sense how I got this, how I thought about it? Question?
You go between 1,000 and 10,000.
I'm going to 10,000. So we want to go up to 9,999. So up till, but not including 10,000, because 9,999 is their stopping point. And this is perfect because like it'll figure out the right one. For the negative term has the 9,999, so we get up to 9,997, and just doing it this way is still fine because like plus 4 is too big for the next one. So that's our positive denominators. Our negative denominators, we want to do 1 over 3, like 3, then 7, then 11, then 15, right? So let's calculate that sequence. That'll be np.arange starting at 3, right? 3 to 10,000, going up by 4s again. This will give me the 3, the 7, the 11, all the way up to and including 9,999. This will be my negative denominators. Yeah? See how I got those? Questions about that? That's useful. And now I want to calculate not just the denominators, but like I want the terms. I want 1 over 1 plus 1 over 5, 1 over 9. Like I want to calculate 1 over 1, 1 over 5, 1 over 9, 1 over 13, all those bad boys together, and I can do NumPy array stuff to make that happen, right? I can say, give me 1 over the positive denoms. Do you see how that's like just like we were multiplying an array by 2? You can do 1 over an array to calculate a new array where each element was 1 over what was in there. 1 over 1, 1 over 5, 1 over 9. All those values are going to be calculated by just saying this. Does that make sense to us? Like, here's the floating point versions of them with the fancy notation that includes like scientific notation to the power of times 10 to the power of what? Pos, so I'll call this pos terms, is that, and then I do the same thing for negative terms. 1 over the negative denoms. So I've now got, sitting in pos terms, I've got 1 over 1, 1 over 5, 1 over 9, 1 over 13 separately as a sequence. And then in neg terms, I've got, because this was our negative denominators, I've got 1/3 in the first element, 1/7 in the next element, 1/11 in the next element, 1/15 in the element after that. So I've got these two sequences now called these names. Does that make sense? Any questions about the progress we've made? Because I'm almost home free, right? My goal is add all the pos terms together, add all the neg terms together, subtract the neg terms from the positive terms. And I've got pi over 4, or an approximation of it, at least. Yeah? So do that. And then I've got, so pos terms. I've got all those elements. I just can't see the fraction very easily. But what I want to do is I want to add them up. So one way to add up all the pos terms together, like we saw before, is I could say pos terms dot sum, like that. Another way, there's a couple different ways to do summation in Python. You can also there's a sum function. Say sum all the things. That also works. So sum up all the positive terms, and then sum up all the negative terms, and subtract the negative terms from the positive terms. See how that's going to give me my pi over 4? So that'll give me an approximation of pi over 4. And if I multiply that by 4, this whole thing should turn into what I wanted. 4 times, like we did it all. We added up. We did it. We kind of like took some things near each other and like made it easier on ourselves. If I do this math, I get pi to 2 decimal places, which is not bad. All right. If you wanted to be more precise, you better believe you can go to like 100,000. Maybe this will give us another decimal place or something. If I rerun all these cells. Ooh, nice. This gives me to 157. This gives me to 4 decimal places. It's not bad. But I had to do 10 times the work. So maybe it's not the most efficient thing. But it worked. So that was our original. We got it to 2 decimal places, just going up to 9,999. But does it make sense to us how I use those sequences to build the denominators I want, and then the terms that I wanted, and to add them together to get the answer I wanted? Cool. Because, yeah, that's powerful and that's fun. Yeah, I don't know. Let me show you a few things, and I think that's all I have to say about sequences. Let me show you some ideas. All right, so I promised that if you ever ask for a column of a table, then you're getting that back as an array, and then you can do array stuff, all the stuff we've learned on it. So let us, for fun, go back to my Pokemon example. So if you want to follow along with this, and I encourage you to, maybe I'll stop and have you try some stuff. You can go to our Jupyter Lite and click the second link that has our data sets, and it also has the Pokemon like ready to go, I think. Then click that link. But let me read in our Pokemon table. It's table.read table. It's in my data folder /Pokemon.csv. And I'll call that Pokemon. Remember, it was very large, and the column names were in alphabetical order, which is kind of useless because I think of the Pokemon like I want to see the name first. It's way over there. But there's my Pokemon table. If you want if you want to call them out of the table, we know already that we could do dot select, excuse me. We do select and you just give one thing, it will give you back a new table with just that column, but that's still a table. So like if I say Pokemon.select the name, the name column as a stir, right? That will give me back in a table again. It's pretty, that's why you can see it's a table. I give back another table that has just the name column, so it's still a table. There's another way to get a column out. You can say there's dot column. You can say table. You give me a table name. Say dot column, and then that will give you the array form. The array form of that column secretly. So dot column works like that. There's that documentation page. You better believe it's here somewhere. Dot column, so give me a table, dot column name. Also indices, we'll get into that in a second. It just gives you the value of that, every value in that column as an array. So instead of this, if I said Pokemon dot column name, I get the array of all these strings. Does that make sense? And then I can do array stuff on them. I could be like, I don't know, go to an item, I could make them all uppercase or something, I don't know. But like I can do stuff on them. So I can say np.char. That was upper. And this like shouts all their names back to me. Like that will work. That will totally work. So this results in the column as an array, as a NumPy array. We can do all the things. If you had a column of numbers, then you could do numerical stuff. You can do all the things that we were doing to calculate pi. You can like add two things together, multiply the answers by 2 or something. But yeah, I just want you to kind of play around. I think we've got plenty of time for that. Let's do, I don't know. I got some questions for you. I'm going to give you this code because I've shown you a bunch of cool stuff that you can do. I showed you like summing and get the average, and there's those documentation pages. So like, let me upload all the code I have right now if you want to go look at it. So if you go to our code from class page, give me, oh no, give me an extra second now. I believe in you. Cool. Then okay. Now if you go to our code from class page, you'll see our chapter 5 file if you want to go look at that. But what I want to ask you to try is we've got this Pokemon table, which you can get yourself if you go to our temporary link. I've got some questions for you, so I don't know. Question 1. Get the average attack power of every Pokemon in the dataset. Because there's a row, or sorry, there's a column called attack. It's here somewhere. It's in alphabetical order. There's attack. So here's the attack values of every Pokemon. Give me the average. So try that. So study this table. There's question 1. Let's do a couple more thoughts and look at the documentation pages, and I'll come around and get you help as well. Let's see. Get the, I don't know. Get the minimum defense value of every Pokemon. Using array operations. So there's a way to do it with just like a dot where and a dot show, or a dot sort and a dot show. Do it the long way. Go look at our documentation page. There's a way to get minimum values. All right. So what's the weakest the Pokemon that's not very good with defense? Go find me that one as well. So yeah, give those a try. I can come around and help you, but you're gonna go and get columns out of this table. Do a dot column operation, so you can scroll up, go to the code from class, see what I was doing. Please help each other. I can also help you. And I think that's what I wanted to say. I try to get the average attack value of every Pokemon. Can you find that? If I do that, get the column out first, and then there's a few different ways to get average. One of those was the dot meaning that I showed in our code. And there's a minimum, the way to get a minimum value as well. Let me search the documentation for that. Give you a few minutes to play around and ask questions, and then I'll show you my answers.
You should have come with before that. To give the
I can't because I need to show these questions, but it's in the code from class. Let me show you how to get the code from class because I uploaded it. Go to our Canvas. Yeah, go to just the modules page, I think. And then you can either click on previous lecture or you go right here to code from class. Click our class name. Chapter 5.
thank you.
So that's everything we did. Then you can scroll through that. I don't know the right word to say there. Is it of every Pokemon? Minimum value out of any Pokemon of any? I don't know the right way to word that. Maybe I just, let's just say that.
What do you want to do? Going back to me. She's going to geography. Yeah.
I don't think geographers are gonna get replaced by AI. So.
It's the right function for the record. It's above Makeover. It's data $8 slash data time slash reference dash MD. It's on the Jupyter Lab link in campus. It's very on its own. It's the one that somebody made in the Oh, your guys' things.
What's that?
Is it like a party?
On the documentation page. So it's on our Canvas. Go to the Jupyter Lab page. And these reference pages. I was opening up both of those.
The full load. Oh, my 4 questions.
What'd you get for the average check? What's 77?
Yeah, about like 77.8. Should probably round that up.
It's a good job. All right, give you another minute to try.
Yeah. What did you do?
Very loud. All right, friends, let us come back. Let's see what we're thinking. What number did we get for this one? What was the average that we found? 78-ish. Yeah. Do you wanna come up here and type your way of doing it in here? Let's see what you were doing. Show us your ways. That is as efficient as I can do. Come on down. It's all yours. Because there's a few different ways. Let's see. There's like some of them have the word mean in it. Some of the words have average in it. There's a way to do it without any of that. I like that we're rounding. That was a great thought. There we go. Very nice. Let's round to the nearest whole number then.
Yeah.
Nice. Awesome. Is that what we got?
Mhm.
If you didn't round, let's round to the nearest 2 or something. Yeah. Interesting that rounding the nearest 2 decimal places does not perfectly round. Round to the nearest 3 decimal places, does that problem go away? No, apparently not. The nearest 4. Well, I guess we're stuck at the nearest whole number or just not rounding in that case. That's really funny. So yeah, that's like the actual answer, but you could round that for sure. That sounds good. That looks good to me. All right. What do we get for minimum? Minimum defense value. 5. Does everybody agree with that? I think we can very quickly get that, right? It's go to the defense column, and then we can say min. That's one way to do it. Does that make sense? And it is 5. Good. Some things that we could do, we're going to do a bunch of these. Of course, we can copy and paste. But, so yeah, thank you for your efforts. Some things that we could do to make this a little bit easier on ourselves could be something like, we could get the whole column and give it a name. We say Pokemon.column attack. You just say that by itself. That gives us the array. And if I want to do a bunch of things on it, I can save that and call that attacks or something. Right? Give anything a name you want. And then it's a bit shorter to do all the things. If you're going to do a bunch of things on this data. So then I can say, instead of NP mean this whole thing, I can call it attacks. So I gave it a name. Right? Gave it a name, and now it's happy. There's a bunch of ways to do it. I think the first way I showed you was say the name of the column, and you could say .mean on it. That would work. np.mean. If you look at the documentation page, one or the other. There's np.average as well as np.mean. Does this one say that too? It does. Yay. So yeah, that's another way to do it. np.average on attacks. Or there's one last, I guess there's a million different ways to do it. There's one last way to do it that does not use the word mean or average. We could just go old school. You can always, how do you calculate average? But add them up and divide by the size. You could sum them up, divide by the length. See that? That would work. So sum up the attack values and divide by the length of the attack sequence. And that's how somebody implemented all those, probably. So that's pretty fun. There's that one. And then, yeah, that's a good way to get the defense value very quickly. You just say min on the column. But you can give it a name. You're going to do a bunch of things on that column. So yeah, I think that's what I wanted to say about all that. Any questions about any of that? See it? All right. Just a couple last few things. We have another miscellaneous section for this chapter. Whee. Boop. I just want to teach you an operation called join on sequences. So if you got a sequence, this is only going to work if your sequences have strs in them. So it can't be the sequence 1, 2, 3, but the strs 1, 2, 3 are fine for what I'm about to show you. If you have, you can, this is like for making output to the user that's easy to understand and digest for them. So you can create a string out of an array of strings by joining them together with a separator in the middle. So the way you do that is you put your separator first. So like I want to print the 1, 2, and the 3 out, or I want to make a string containing the 1, 2, and 3 together in that order, and I want to separate them with a comma space. So I'll make a comma space string, and then I'll say dot join, and then I'll put the sequence that I want to join with this in between them. Does that make sense? And the sequence, it has to be of stirs. It won't work otherwise. And this will shove the comma space in between each of these and generate a new string that has all this. So that's useful if you want to output this to a user of your program. And then, yeah, you can put whatever you want. I'll just put it in the middle. You just be like space and space. Use that to join together all those values in that array. So now it's going to make the stir 1 and 2 and 3. That kind of makes sense. You'll need that for an eventual homework/lab. And I think that is all that I wanted to say about sequences. And that will be your chapter 5. Any questions about any of that? Anything that we covered today before I let you go off and work? Because I think that's all I got. I got no new assignments to assign due dates for. Remember that I gave us like the order of assignments and one of the slides from last time. So they're all out there if you want to get started early, but we have not completed all of the knowledge to like give us a final due date for something new. But we have due dates for homework 0 or homework 1 and lab 1 right now. You want to do lab 1 first. But I think that is officially all that I wanted to say. So I'll give you all this code, this video, these slides, and yeah, all the rest of the time now is yours to work and ask questions and take your break whenever you want to.